Let's look at a few other basic things. Start with this animation of sea surface temperatures, or surface temperatures, not just sea surface temperatures. We looked at the mean when we opened this chapter. This is just showing the seasonal cycle. So it's going through a number of years from 1979 to 2000 average. So that's a climatology. And you see much better now the interplay between atmospheric circulation changes due to seasonality that we talked about in terms of solstices and equinoxes, and we will add more details about what happens with these temperature changes in the ocean and land and so on. So what do you notice most is that when you start in the beginning of the year, warmest waters are to the south, for example here, and they seem to move to the north with the sun and then come back with the sun. What is happening is that the tropical heating, even though tropics has 12 hours of day and night, sun is moving north and south, and ocean is able to move north and south, and we'll see that the wind bands are able to move north and south. So that creates warmest temperatures, and that tends to create a band of rising air on the warmest temperatures. Remember, we talked about how warm temperatures lead to rising air, humidity, expansion, condensation, clouds, rain, and then circulation. So that's very clear here, even over the Indian Ocean, which remains mostly warm. But here you see a nice contrast. As you come into the summer months, you see coldest waters begin to appear and warmest waters remain here and to the north. So as the sun comes in the boreal spring months, this gets the warmest of the year, even though it'll still be not as warm as in the west. So upwelling is what we will see later on, which is related to winds and Coriolis effect. So you can clearly see that there is a very strong seasonal cycle also along the coast. So if you now compare the temperatures along this coast here versus this coast, you can see that the temperatures here in the, let's say, boreal summer month, very warm here, much colder here. The contrast is very obvious, and you also get cold winter temperatures here, and even during the summer they remain relatively cool, and the seasonal contrast is also different across the more humid places versus the drier places, and it's of course the same for the deserts and other places. So you can pick any favorite region and see how temperatures go back and forth with the seasons. So you can watch this animation as long as you want to just recognize features, and it turns out that of course this is on the web, so you can see this one and the rainfall and see the relation between them. I will show the rainfall animation in a little bit. So along with this go things like these. These are basically water vapor. You can see that we said warmest temperatures tend to be where air rises, water condenses, so you can see those, and then you have other processes happening here. If you get into deep dynamics, you will learn why these things have this kind of a south west northeast tilt. Depends, it is related to the dynamics of how energy gets moved from the low latitudes to high latitudes, or energy deficit regions to energy surplus regions, and the fact that when you move the air from lower latitudes where the earth is rotating much faster because it's larger area that has to go once around in 24 hours, whereas here it's a smaller circumference in 24 hours, so things have to move fast here to cover large circumference in 24 hours compared to here. So if you move a parcel of air from here to there, there is something called angular momentum conservation, so it begins to move faster and faster as you go to smaller radius of the earth. So we will touch on that a little bit, but you can clearly see these features here. So this one is focused on the Atlantic, this one is focused on the Pacific. Here you can clearly see this rain band here. The rain band is also there, but it's not that obvious. This is the largest rain band you'll see here, and the warm western Pacific that we saw multiple times moving back and forth with the sun also has 5 meters of rain that I mentioned before, and then you get these other complicated swirling motions. Okay, this is what happens on rotating systems. Everything looks like swirly features. So let's go back to the basics then. We kind of oriented ourselves with the flow features. The very basic is to think about the pressure distribution in the atmosphere. At the surface, pressure is high. It's 1013.2 millibar on average. So you can see it in inches here. So with height, pressure drops off exponentially and remains very low at once you go above about 30 kilometers or so. So the atmosphere becomes very rare, very few molecules running around, which means the sigma T to the fourth will be very small because there are very few molecules to emit radiation. So we will see how the definition of troposphere and stratosphere come about. We won't touch much on mesosphere and thermosphere, so there are reasons why they are called those things. Troposphere is where tropos is where it's overturning, so we have weather. Stratosphere is where it is stratified, so it has very little weather. And the temperature gradient looks like this. So we will look at various versions of these. So again, we are looking at surface into the upper atmosphere. So here you have showing temperatures in degrees centigrade and degree Fahrenheit. So you have the outer limit here at 1000 kilometers. This cannot be degrees centigrade. So this is pressure here, and temperatures are shown here. So you go height is shown here. Sorry. So you go. Okay. So you have the warmest temperatures at the surface. Temperature drops off with height, and then it begins to warm again. So you see it much more clearly here. 20 degrees centigrade or so near the surface as a global average. Decreases to about a few kilometers depending on where you are, as we will see, and then temperatures begin to increase again. So this is the troposphere. There is the tropopause, and then warming temperatures into the mesosphere, and then cooling again, and then in the thermosphere increasing again. So we'll ignore these and just focus on these here. As we saw before, where the energy gets absorbed, the ultraviolet is getting absorbed almost completely by the atmosphere in the stratosphere, because those high energy photons are able to split the oxygen molecules and create oxygen atoms. Oxygen atoms combine with oxygen molecules to create ozone molecules in the stratosphere, and ozone absorbs blue UV as well. So you essentially have a warming happening because of these reactions and because of absorption of UV by ozone, and that's what warms. And the gradient change here makes it harder for the air to cross across the tropopause into the stratosphere, and that matters a lot also for how climate and weather behave. So if you look at the tropopause from the low latitudes to the poles, you can think that the temperatures get colder and colder as you go to the poles. So the atmosphere is getting more dense and compressed. So you can see that the tropical tropopause is starting at warm temperatures, goes up to 15 kilometers or higher, and then comes the tropopause and the stratosphere. Whereas if you go to middle latitudes here, the temperatures are colder near the surface than the tropics. The tropopause is lower, and then stratosphere starts earlier. As you go towards the polar latitudes, the temperatures are much colder, minus 20 degrees centigrade, and the Tropopause is much lower at around 7 to 8 kilometers, and there is the stratosphere. So this is very important to remember, that the height of the tropopause drops quite sharply from the low latitudes towards the poles. So you are squeezing the atmosphere into a smaller troposphere as you go towards the pole, and this also matters for various processes and how circulations get set up. Okay, so let me leave that introductory part there, and then we will start to add more dynamics on how we begin to combine the need to move energy and rotation and Coriolis effect. This is kind of the critical part of how we understand atmospheric circulation. Again, this is a very introductory course, so we are doing it in a very simple way. You can learn much more of the dynamics in my other courses, but you don't have to worry if your main focus is not the physical climate science, but applications of climate science to other things. Okay, I cannot emphasize that enough. Just get a good sense of these basic processes so that you can go to your specific field related to climate science. Okay.